Hi. My name is Alexandre Champagne. I'm from the University of Montreal, Canada. And today I'm going to be talking about a simple physical phenomenon who could have been an overlooked driver in prebiotic complexity. So let's first discuss two well-known problems in origins of life research. So we've been studying the reactions that led to life for several decades now, and we've got a pretty good understanding of how they work. But you know, these chemists, they have it really easy in the lab with all these purified chemicals and ideal lab conditions. But if you think about it for a minute, the prebiotic earth was rather a mess, and the concentration of these chemicals must have been rather low, which suggests that we must have needed a process to at least increase the local concentration of reactants, such as, for instance, compartmentalization. Now, several options have been suggested, but none of them is completely general or definitive. Okay, thank you. Okay, so this is problem number one. So a second problem, a second problem is that of cooperation and its opposite, parasites. So both cooperation and parasites appear at all levels of biological organization. Clearly, we've talked about cooperation earlier, we need cooperation to build any complex thing. The cells in your body don't compete, otherwise you wouldn't be able to survive. And in the same way, we have observed parasites emerge in all Darwinian environments. Parasites are simply free riders that exploit the abilities of other entities without providing much to the group. So being a parasite is easy and rewarding, right? Which is why explaining the emergence of cooperative behavior is such a long-standing issue in biology. Now, I've said that a few solutions have been suggested, but none of them is completely general or definitive. But what if we could try to offer solutions to these issues thanks to a very simple and widespread physical phenomenon? So how do we go about modeling cooperation? We can use the prisoner's dilemma, which is a model in game theory where two players facing each other can either choose to cooperate or defect, either favoring the group's success or try to exploit each other selfishly. This model has been used in biology for several decades now in studying animal behavior and at smaller scales as well in explaining the dynamics of bacteria and viruses. So some simple strategies at the prisoner's dilemma include unconditional cooperators, unconditional effectors, and reciprocal cooperation. Now, a few words about this last strategy, reciprocal cooperation, which is also called tit for tat. So it's one of the most powerful strategies. What tit for tat does is very simple. You start by cooperating with your opponent, and then you just reciprocate whatever your opponent's been doing. So you just mirror their last move. So it's a very simple and very powerful strategy. It's been shown to be widely successful against a wide range of opponents. So I've said it's one of the simplest strategies. In fact, it's the simplest memory one strategy, meaning that it only takes one bit of information to encode, which could likely favor its emergence in nature. But there's one major limitation about tit for tat. It cannot tolerate errors. So let's say you have two TFT players facing each other. They cooperate, everything goes smoothly, and then one of them makes a mistake. Then they will both end up in this endless cycle of defection, which is the worst outcome to the IPD. So how can we model the emergence of cooperative behavior in nature? So one thing we know about prebiotic chemistry is that the substrate matters, right? But we're physicists, so we don't care about approximation. We'll just replace that with a simple lattice. On this lattice, we're going to distribute a large number of players that are going to behave with their neighbors according to the strategies we just described. We'll then bring Darwin in the mix and replicate the most successful strategies. And finally, and again, since we're physicists, we're going to bring a little stochasticity in the mix and make sure these strategies make a few mistakes. So what happens if we carry out simulations using this model? what we can do is vary the error rate of the players. Now, I've mentioned mistakes leading to an error rate. And as we vary this error rate, we get patterns ranging from fractal structures to filaments to islands of cooperators. Now, one thing we can observe using this model is the variation in population frequencies as we vary this error rate. Now, you can see that for most of these simulations, we end up with a mix of cooperators and effectors, which is partially a reflection of the fact that TFT cannot deal with errors properly. Now, this model is already pretty complicated. It's also computationally complex. So we'll simplify things up a bit for a minute. Another type of model we use in statistical physics is called the mean field approximation. So pretty much like you can approximate the thermal energy of a large number of particles in a gas using one single metric called temperature, you can represent the average behavior of a large number of players through differential equations. And one thing which is pretty interesting with that type of model is that you can quite easily investigate the effects of molecular diffusion in these simulations. But what is molecular diffusion anyway? It's simply the physical process by which every physical system gradually tends towards a state of equilibrium. So as you include diffusion in these kind of models, what you get patterns. And as you vary the diffusion rates, you get different characteristic scales. Now, what you're getting here, in other words, is pattern formation or structure formation. And transposing this on a prebiotic Earth, these structures could very well help in separating chemical species, pretty much like thermophoresis does, or phase separation. So, I don't know if the animations are gonna play. Yeah, okay, there you go. Okay, so now we've seen pretty patterns appear in these simulations. So we can go back to our discrete model and try to do the same thing. And one way we can include diffusion in the discrete model is use what we call diffusion by interchange. And in diffusion by interchange, we're simply going to swap players randomly on the lattice, which is the discrete equivalent of the continuous molecular diffusion we just saw in the previous model. And as we include diffusion in the discrete model, what we're seeing is a series of regime changes. So for instance, at lower values of the diffusion coefficients, what we're seeing are islands of defectors swimming in a sea of cooperators. Now, if we increase the diffusion coefficients, what we're seeing are larger patterns appear. But the important thing to notice on this figure are the two narrow blue bands you see towards your right at the bottom of the figure, which means that as we increase diffusion to very high values, TFT completely takes over the whole system. It invades the system, establishing cooperation. So this is what these simulations look like with spirals that are similar to Turing patterns. So now if we want to make this analysis more quantitative, we can take a look at the population frequencies for the simulations we've just talked about. So on the horizontal axis, we have the diffusion coefficient, and on the vertical axis, we have a range of error rates. On this figure, we've made unconditional cooperators diffuse much more faster than the other strategies. And you can see that we still have a lot of parasites in the system. We also recover the two blue bands that we saw in a previous figure. But now, if we make, for instance, TFT diffuse much faster than the other strategies, the situation changes dramatically, which means that there's a lot more cooperation in the system, and TFT even invades the system for a large region of the parameter space. So what you need to remember from this slide is that diffusion can change dramatically the evolution of strategies in these simulations, and it can even favor cooperative behavior from emerging. So going back to the beginning of my talk, we were looking for a process that both creates structures and can favor cooperative behavior. And it appears that diffusion perfectly fits the bill. It applies to any physical system. It can create structure, and it can favor cooperative behavior from emerging. So instead of thinking about diffusion as some boring physical process that makes everything equal and could even prevent the origin of life, diffusion could very well help in creating structure and be a prebiotic driver of complexity. And with that, I thank you for your attention, and I will take any question.
Thank you, Alex. We have some time for questions. There are also empty seats up here in the first row for those of you in the back. Please.
Your last statement was that diffusion is a driver of things, but wouldn't it be better to say that limited diffusion is a driver of things? That fast diffusion is a mixer, which doesn't give you what you want, right? So it's...
Yeah, if you increase diffusion to past some critical point, you get a well-mixed system.
Yeah, so the argument is really
Yeah.
I would have made the opposite conclusion, that limited diffusion is important, or that encapsulation in separate compartments is important. There's some reason for not getting mixing.
Yeah, well, for instance, in this figure, what you're seeing is that, so as we increase the diffusion coefficient for unconditional cooperators, we have to increase to very high values of the diffusion coefficient for TFT to take over. Whereas, since these are logarithmic scales, when we play with TFT's diffusion coefficients, cooperation takes over more rapidly. So this is the difference when we're playing with TFT's diffusion coefficient versus ALC's diffusion coefficients. So what we're arguing here is that depending on which species diffuses faster, we're seeing an emergence of cooperation which happens much more quickly, which is basically the difference between these two figures.
Is there a reason why they would diffuse at different rates?
That's a good question. The analogy here is that these species playing the iterated prisoner's dilemma could represent different chemical species. So depending on the morphology, or they could diffuse at different rates. So yeah, but of course this is an idealized model, but this is the analogy here. Different strategies would represent different chemical species, which would have different physical properties. And if some of these species would diffuse faster, then we have a differentiated outcome in terms of cooperating behavior. Yeah.
All right, 2 more quick questions.
Okay, Martin Rahm from Chalmers. I have a bit of a naive question on this tit for tat. You mentioned several times that it's sensitive to errors.
Yeah.
Is that like a realistic in a real setting? Could an actor not be responding to the average behavior of its neighbors? Say that you allow for some errors and just take a decision based on the average.
Well, the simulations we've done here are based on the iterated prisoner's dilemma,
yeah.
And with games that are played for a large number of rounds. Specifically, what we wanted to do is try to reach the point where the number of rounds did not change the dynamics of the system. So specifically in these simulations, they're playing for 2,000 rounds.
So it doesn't matter too much, is what you're saying?
Yeah, so
okay.
yeah, since they're already doing, so this is really the iterated prisoner's dilemma. They're already playing for a large number of rounds. So they're reacting to the average number of errors, indeed. Yeah.
Okay, thank you so much.
Mm-hmm.
Hello, Shelby Osborne, University of Arkansas Center for Space Planetary Sciences. I was just wondering, with your iterated prisoner's dilemma, are you maybe, like if you take this a step further, maybe potentially incorporating a nearest neighbor's adjustment to where you can get a full view of how diffusion rates can affect each other across the diffusion coefficient log?
I'm sorry, I'm not sure I understood your question.
So you know how in your next slide you have those boxes of diffusion rates and you have those two blue lines that show like when diffusion takes over? Yeah, so nearest neighbors can kind of give you a better idea of how that transition occurs instead of such a blunt transition. Just kind of to give you an idea of like how a better idea of how the diffusion rate will change and interact as it truly moves along. Do you think that's something that your code could incorporate, or is that not something you're really wanting to look at here?
So if I understood correctly your question, would we be able to visualize the transition more clearly than, yeah, this is why we have created these two figures to try to represent, because we have several parameters, so we're trying to represent the system's behavior in a multi-dimensional space. And it's always hard to visualize these transitions because you have n-dimensional spaces. And this was the clearest way we could find to represent the transition. Yeah.
All right, great. Let's thank Alex one more time.